LiDAR, or light detection and ranging, sends short laser pulses and measures their return time to compute distance. Combining distance with angle produces 3D or 2D points that map the scene. LiDAR's ability to generate point spaces is essential for route planning, obstacle avoidance, terrain mapping, and feature detection, making it a core technology in robot vision. For our design systems project, we are building an autonomous robot to locate and retrieve target blocks. The performance and accuracy of the supplied SLAMTEC RPLIDAR will determine how we integrate it into the navigation stack. Either paired with an RGBD camera for visual SLAM or used alone as a proximity flag for minimum obstacle separation. Hence, to quantify the LiDAR's suitability, we measure key parameters: the minimum reliable range, how readings vary with distance, the effect of surface reflectance and lighting, and the occurrence of anomalies or outliers in the reported ranges. We measured the distances reported by the LiDAR for white and black obstacles placed at known, straight-on positions and compared reported ranges to true distances to quantify accuracy and error. The protocol did not account for real-world error sources such as uneven target surfaces, glare from glossy black materials, the white-to-black samples not being perfect proxies for the color spectrum, and variable room illumination. Our initial setup produced corrupted readings because the LiDAR was floor-mounted near people, chairs, and lockers. Moving objects and stray reflections from off-axis directions contaminated the experimental data. So in our next setup, we masked the LiDAR with large black panels to block stray reflections, moved it to the tabletop, and increased lighting so the sensor captured cleaner returns from the target area. Separately, we shortened each run from 30 seconds to 5 seconds to keep conditions static and collected data for white and black targets at 0.2 meters, 0.3 meters, 0.4 meters, 0.5 meters, and then every 0.5 meter up to 3 meters. All scans were recorded from the ROS topic scan and saved to separate ROS bags for offline analysis. The initial stage of data processing consisted of acquiring raw data from the ROS bag file in the form of a CSV. After establishing the procedure for navigating the raw data and selecting target points within a defined span and range, we proceed to apply filtering to the data. Our filtering app narrows raw LiDAR points by restricting the angular span to 178 to 180 degrees and the range to plus or minus 0.05 meters, producing near identical distance readings given the 0.225 degrees angular resolution. Regression analysis of the points derived from the white target shows they are highly accurate, with nearly all points within a 1% tolerance. The measurements show a linear relationship with the true distances, so LiDAR readings can be used directly without bias correction or scaling. However, measurements from the black target show inconsistent, non-linear deviations caused by low reflectivity and increased absorption of the LiDAR beam. This increases LiDAR non-linearity beyond about 1.5 meters, so corrective measures are required. There are additional irregularities, a 1-degree blind spot across the 180 degrees to 179-degree wraparound, varying minimum detection distances, and edge smearing beyond 1.5 meters caused by beam spreading. Thus from this experiment we infer that the LiDAR is reliable for 0.25 meters to 1.5 meters without biasing and is suitable for precise boundary mapping in the 6 by 4 meter white wall test area.